Okay, so we should probably get started so we stay on time. So welcome everybody to Astrofest 2022. It's hard to believe that this is our first time getting together in 3 years. Time has just flown by. And those of you that were here for the 2019, the first Astrofest, I think will have warm memories of how much fun it was to actually hear about each other's research. And I think that's one of the things that we aim for, is to be able to celebrate and share what's happening here on campus. So in 2020, of course, we had to interrupt our planning quite abruptly. Last year we were virtual. We even did a poster session on some website. What was that website? GatherTown, yeah. Yeah, so is that the future of conferences? Roblox? Anyway, it's 2022. We're done with the pandemic. Well, pandemic's not done with us, I think. But in any case, we are glad to be back here together. And just so you know, we have an oral program until 2:30. And then we'll have the poster session outside. You've probably passed the posters already on your way in. And we'll have some refreshments out there as well, so I hope you stick around. So part of our tradition is to start off the Astrofest with a talk from an alumnus or alumna who can tell us a little bit about their experiences after they've left us. And here to introduce this year's speaker is Professor Paul Ricker.
Thanks, Tony. So our first speaker is Rukmani Vijaya Ragavan. She was a student of mine, got her PhD in 2015, I believe, and went on to an NSF postdoctoral fellowship with Craig Sarrazin at the University of Virginia. And after that, decided that she wanted to go into public science policy, and she did a one-year AIP Congressional Science Fellowship, working in the office of a representative from Washington State, and then a one-year stint in the U.S. Department of Energy as part of a AAAS Executive Branch Fellowship. And the Department of Energy experience led to a permanent job, and she now works with the Office of Energy Efficiency and Renewable Energy Water Technologies Office. And she's going to tell us about how the federal government funds innovation and how you can be involved. So, Rukmani.
Yeah, thanks everyone. Thanks for being here, and thank you, Tony, for inviting me, even with all the trouble that took. As Paul said, this slide basically goes through everything Paul just said. So I was a grad student here. I graduated in 2015. I worked on simulating galaxies in cluster environments in cluster mergers. This is a snapshot from one of my papers that shows how galaxies, experience ramp pressure as they move through a cluster. And then I went on to UVA for 3 years where I was a postdoc. In addition to my research, a lot of what I did was also outreach and advocacy, which put me on the path to science policy. I ran a camp for middle school girls in science. I was involved with this group called 500 Women Scientists on advocating for more inclusion and equity in science for women. And then I did I wasn't sure what I wanted to do next. I applied for academic jobs. I also heard about the science policy route. So I applied for a congressional fellowship that's administered by the American Institute of Physics. This is a one-year program that places you in a congressional office, and you get to work on policy on federal policy and legislation. And I worked on some legislation related to computer science education. I also worked on appropriations, which I'll talk about in a second, related to STEM education, to clean energy. I also worked on aviation and housing, which have nothing to do with the others. The office just needed someone to work on those issues, and I was available, so I said, sure, I learned about aviation policy, so I can also speak to that. And then I, decided to stay in DC. Government was interesting, went to DOE, and then now I work on innovation and commercialization, which is essentially funding programs related to these in DOE. So I'm going to talk about how the federal government funds innovation, and that has to start with what the federal budget is. So, we don't need to spend too much time on this, but the federal government has revenues. This was from FY 2019, which is why I included. And the reason I have the FY 2019 budget here is because the last couple of years were a little unusual with all the COVID funding. But typically, the federal government has around $3.5 trillion in revenues. These are all income taxes, payroll taxes, et cetera, and spends around $4.4 trillion a year. And this is everything. This is about more than 50% of this is what goes into mandatory spending. So this is things like Social Security, Medicare, Medicaid, which the government is obligated to by law every year. And the rest of it, and about 30% of this, is what is called discretionary spending. And this is what the government has to budget for and decide every year. A little more than half of that is on defense. Less than half is on non-defense, which is everything, including energy, science, transportation, et cetera, et cetera. And the final pie chart on the right is the R&D budget. So again, around 40% of the R&D budget goes to the DoD, and the rest is between the different science agencies. So HHS, this is mostly NIH, is around $40 billion. DOE, where I work, is around 19. NASA has around $14 billion in R&D spending. NSF is around 6.8, and everything else is in this tiny graph. So R&D spending, the point of this is R&D spending is a very, very, very tiny fraction of the overall federal budget. And so the way funding works through Congress is there are these two. So at least the discretionary part of it is basically decided by these two committees, one in each chamber of Congress, called the Appropriations Committees. And so there are 12 subcommittees within the Appropriations Committee, and these don't necessarily correspond to specific agencies. So for instance, Commerce, Justice, and Science includes the Department of Commerce, the Department of Justice, NASA, NSF, and a few other small agencies, and they get to decide how much money each agency gets, and also the different programs within each agency. Energy and water, which funds us. The DOE also includes a few agencies within the Department of Interior, and so on and so forth. And each of these 12 subcommittees releases a bill every year, which basically sets out how much funding these different agencies get. In addition to the bill, the really fun part is kind of buried in something called a report. So the committees put out reports that say, okay, you get this much money, but this is what we really want you to do with the money. And agencies are usually obligated to stick to that. So the snapshot in the middle is for astronomy, and I just snapped this a few days ago. And there's usually not a whole lot of direction for astronomy from Congress for many reasons. So most of what was in the direction this year, this is in something called a conference report, was just do what the decadal survey tells you to do. But some other agencies like DOE receive a lot more congressional funding. So this snapshot is from our office, the Water Power Office, which has a lot of direction down to the $5 to $10 million level. And so we need to really figure out how best we can stick to this direction. And that dictates what we can do when we fund R&D programs. So now in the executive branch, which is where I am, budgeting is a little bit different. So the president releases a budget every spring, and that's usually around February or March. The FY23 budget just came out, and that's usually just before the State of the Union happens, if you follow that. And that is the president's budget is essentially a wish list of everything they want to do in terms of, where they hope to raise taxes from, where they want to cut taxes, increase taxes, and also where they want to spend money. And that's pretty high level. It's a few hundred pages long. But every agency also releases its own congressional budget request. And if you're interested, I strongly encourage you to read these. These are hundreds to thousands of pages long, but you can search for the specific program you're interested in. And, and this is what our office is focused on. So these are, again, down to the millions of dollars level, where we say, this is what we did in FY21 with the money you gave us. This is what we want to do in FY22. And we want more money because X, or sometimes it's less money because some programs are wrapping up and we want to do something else, and so on. This is a snapshot of how this works in the astronomy-related agencies. So, for instance, NSF released their budget request a few weeks ago. I've highlighted this table for astronomy. There's not a whole lot of detail, but, NSF and the president's budget includes only a 1.7% increase for astronomy this year. With a caveat, this is the president's request. This is not the final number. Congress gets to decide the final number, not the president, not the executive agencies. Similarly for NASA, this is, the yellow bars are the president's request over existing levels for the different NASA programs. So that's NASA Science, all of astrophysics, that includes JWST, heliophysics, earth science, and so on. So finally to DOE, where I really am. So this is a huge agency. We are about a $40 to $42 billion agency usually, although this year we received around $60 billion in the infrastructure bill, which we need to spend over the next 5 years. So that's changed things a little bit. But I'm in this little box highlighted here, which is the Office of Energy Efficiency and Renewable Energy, which is under something called the Undersecretary for Science and Innovation. An easier way to visualize this are the program offices, and these are basically the offices that get to send money out to fund R&D and other work that DOE does. And so our office is one of those that gets to spend money out. So I'm not going to say energy efficiency and renewable energy because that's a lot. I'm just going to say EERE. And so EERE, what we get to do is basically anything that relates to clean energy and anything that touches clean energy. So that's divided into transportation, renewable energy, and energy efficiency. So I'm in the water power office, which is one of the renewable energy offices. We get to fund R&D in hydropower, which is what you're probably most familiar with, right? That's dams capturing energy from water flowing down a gradient. And we also support marine energy, which is a lot less mature. So that's capturing energy from waves and tides and currents, and that's a lot more challenging for many reasons. And so that's a much earlier stage R&D program, and it's also really exciting. And so these different lines highlight, again, our historic budget levels, what the president requested for fiscal year 22, what the House wanted to give us, what the Senate wanted to give us, and what our final number was, which is lower than what both the House and Senate wanted to give us, because sometimes that's just how it works. And so what we get to do in FY22, in fiscal year 22, is spend this $162 million effectively and efficiently to fund all the R&D we want to do in a year. And the way we make those decisions is through, we have a multi-year strategy, we have annual strategies, and we have these different activity areas in each of our different programs. So for instance, in marine energy, we have our activities that's foundational R&D, like some system design and validation. A lot of what we work on is reducing barriers to testing, because a huge part to making things work is testing them, making sure they don't break and so on. And access to the data, so making sure that as much information is publicly available as possible. And we also have these long-term missions and visions that guide everything we do. Vision is we need a U.S. industry that expands our energy portfolio, and our mission is trying to do everything we can to deploy systems at low costs. And at the same time, we also have these other objectives that are mitigating climate change. The Biden administration has a goal of enabling a 100% clean energy future by 2050. And we also want to power underserved communities, enhancing resilience, making sure that the benefits of our work fund everyone equitably, and also accelerating technology development timescales through various R&D activities. So to fund these activities, we have different types of grants and mechanisms at our disposal. So I'm sure most people in this room are familiar with what foundational lab research or foundational university-based R&D involves. But that's a small amount of what we do. We also use these things called small business innovation grants, which are specifically aimed at small startups and smaller businesses. We have these things called prizes, which are really fun, and we are really starting to ramp up our use of. A prize is essentially if you meet a goal or if you meet an objective, then we cut you a check, and you can do whatever you want with the check. It's not a grant. We also offer fund labs to offer technical support. And when I say lab, I usually mean national labs. So DOE has 17 national labs, including labs like Argonne and Fermilab. And so we fund these labs to do different kinds of activities in addition to R&D. And we also have other financing mechanisms I'm not going to get into. And we have these like contracts and cooperative agreements. And these different types of activities are mechanisms are used to fund different stages of research. So there's early research, which is what we do in basic science, but when you work in applied energy, you also need to really test, demonstrate, and make sure those systems are viable so you can eventually commercialize those, attract external investment. There's only so much the federal government can do, and eventually make those marketable. So prizes, I briefly mentioned these. These are some examples of prizes that I've helped run in my time in the office. And these are usually aimed at specific technical objectives. So one is this Waves to Water prize, which just concluded a few days ago. The goal of this prize was essentially to use wave energy to power desalination systems. So as I said, wave energy is really technically challenging because you're really trying to capture the bobbing motion of the waves and try to convert that into useful electric power. And so this is really expensive, this is really challenging, but there are a few opportunities where it makes sense as cost competitive energy source, especially when it's co-located with the resource. So seawater is usually where you have waves, and so if you capture those waves and you desalinate, and you figure out a way to effectively desalinate seawater, that's a way to get wave-powered systems out in the ocean. So, we ran an open water test. We had around 67 teams participating as of 3 years ago, and then we had multiple stages where you had to demonstrate the feasibility of your system, and we eventually had 4 finalists build and test their systems out in the open ocean. This is a different prize that is using, again, wave energy to power autonomous underwater vehicles. Because again, you have these things in the ocean. The ocean is where waves are. So if you can figure out a way to harness the energy of the ocean to power these AUVs, then that's again a cool proposition. And then I briefly mentioned these things called Sbir or Sdtr grants. So these are for small business-led R&D. Again, this is in applied energy, less so for basic science. But the goal of these is if you're a small business with a viable idea, then you can get a $200,000 grant to establish merit and feasibility. It's about a year long. And then once you do that, you should be able to apply for a bigger grant of about $1.1 million to actually refine your design and build a prototype and prove the viability of your concept so you can then commercialize it. We also have a similar model for national labs where we give lab researchers around $50,000 to $100,000, and this is especially something aimed at junior researchers who don't have a lot of experience in applying for grants. And then with these small grants, you can you can basically lay the foundation for R&D. I have just one more slide. And then, and this is a way to engage junior researchers. Another thing that is something that I am really interested in and spending a lot of time on at the DOE level is really making federal funding more inclusive and equitable. And this is something that I've been, really influenced by my time as a grad student and a researcher, is making sure that federal funding isn't just out to people who have the resources or the institutions that have the capabilities to really be able to apply for these huge research grants. And, we ran a request for information a few months ago where we asked people in the community, what are your barriers to applying for and receiving federal funding? And how can we make sure that disadvantaged communities, underrepresented groups can mitigate those barriers? So, this might be familiar to many of you in the audience, but we heard issues like, it's a large time commitment, the application process is incredibly complicated, the eligibility criteria are often unclear, et cetera, et cetera. So we are working on a number of different things to help address these issues, one of which is this prize called the Inclusive Energy Innovation Prize, which is our $200,000 awards to people and to organizations that are creating pathways to disadvantaged communities and DOE. So it's a little different from some of the more technical prizes I mentioned earlier. So finally, if you want to do what I do or something similar to what I do, these are some things that can help you. So if you care about the federal budget that directly affects your research, if you're anyone in this room, then you can call your congressional representatives. And that was something that I did when I was in Congress, was work with a lot of stakeholders, with students, with universities, to understand what their research goals were. And now, around March, April, May is what is called appropriation season. And this is when the appropriations committees I mentioned earlier are writing their bills and their reports on deciding what the next year's fiscal year budget is going to look like. You can also engage through the American Astronomical Society or any other professional society. They have these congressional visit days, which I strongly encourage anyone interested to do. I did that a few years ago when I was a postdoc. It was an eye-opening experience. It was very interesting. Something else is just staying aware of what is going on in the funding world. So the American Institute of Physics has this newsletter, the FYI newsletter, which is a really comprehensive and thorough resource for anyone interested in what is happening in R&D at the federal level. And finally, the federal government really, really wants and needs people with training in science, people with scientific training. And it's not necessarily to do science policy, but it's also to apply your skills in research, your skills in synthesizing large quantities of data, and understanding a wide range of issues. So I applied to, and I got the American Institute of Physics' Congressional Fellowship. The American Physics Society also sponsors 1 or 2 congressional fellows every year. And AAAS, which is the American Association for the Advancement of Science, they are the organization that publishes Science Magazine. They also have the Science and Technology Policy Fellowships, which is how I went to DOE. So, yep, that's all from me. Thank you.
Thanks very much, Rukmani, and thanks for showing us a very good and useful path for people with PhDs in astronomy. Do we have any questions? We have some, mics. So if you have a question, please raise your hand and the mic will come to you.
Hi, I'm just curious if there's anything that you learned in grad school that you kind of apply on a day-to-day basis to what you're doing in the government now.
Yeah, many things. So one thing that, is really useful is really being able to do a lit review and putting together a quick summary of what is out there. So I mentioned we ran this request for information a while ago. We had a few thousand pages of responses, and then myself and a few other PhD science fellows put together this report that comprehensively synthesized all that information, right? That was really useful. I think one thing that also occasionally comes in is just having the experience as a researcher, as someone who's applied for grants, as someone who's been a student, as someone who, when I was a grad student, I did not apply for the NSF grad fellowship because I thought there was no way I was going to get it. I thought I was not qualified at all. And then, a few years later, I got the NSF postdoc fellowship. But I think having been someone like that who found the process so intimidating, and now being on the other side, it helps me make the process less intimidating for people who may not know that this is something for them, that this is something they can access. So, yeah.
Thanks, Rukmani. So one thing which might be a little intimidating for someone moving into a role like this is the feeling that I'm going to be overseeing these programs where I don't really have the subject matter expertise, marine energy or something like that. So could you address that a little bit? How how much we really need to have in order to effectively look at these options?
Yeah, I mean, you can definitely learn on the job, right? I knew nothing about marine energy when I came to this office. There's a lot of learning and reading you can do on the job. But a lot of what we do is we work very closely with people who do have the subject matter expertise in the labs, and these are people who do R&D in marine energy. We also work with expert reviewers, but a lot of what we get to do is essentially map DOE's priorities and EERE's priorities into making sure we have the most effective type of solicitation that then researchers can apply into like a funding opportunity. So for instance, we care about net zero by 2050, right? And we really want to accelerate clean energy technologies. So that means, at least for me, we fund the foundational R&D, but we also think about how do you get private investors involved? How do you help a researcher or a scientist who has a technical background but has never run a business? How do we help them learn about how to set up a business, and how do you connect them with the right people? How do you provide access to testing? So a lot of that is management and connecting with the people who have the facilities and enabling scientists to get access to those testing and validation facilities. So these are all skills that you don't need to have a technical background for, but of course, again, if you're someone who likes to learn, then as anyone with a PhD does, then that's not a challenging thing to do. Yeah.
Any more questions? Okay. If not, let's thank Rukmani again.
Thanks.
Okay, so the rest of the program is short talks, and so those of you that are giving talks, I'll be giving you a 2-minute warning before your time's up. And actually, we have Colin Burke up next, although is that okay? It doesn't matter a great deal, but we'll try to stick with the order in the program. So Colin is a 4th-year grad student in astronomy, and he's going to be telling us about NGC 4395. No? Yes.
That's part of it.
That's part of it. Okay. Yeah, I think we're almost there.
Slides before that. Yeah.
All right.
Okay, thank you very much. Thank you, Tony, and to all the organizers. It's great to be back in person. Let's see, how can I advance the slides? Okay, great. So I'll be talking about my work on NGC 4395, and in fact on accretion disks in general. In particular, I'm looking at the optical variability of accretion disks. So this is NGC 4395. It's a beautiful nearby Seyfert galaxy, and it's an archetypal dwarf active galactic nucleus. So I think if you don't know, an active galactic nucleus, or an AGN, is a supermassive black hole in a galaxy, and that supermassive black hole is surrounded by an accretion disk. I'll show you what we can observe from that accretion disk here in a minute. So on the right here is a photo from a ground-based observatory, and on the left is a photo from TESS, which is the Transiting Exoplanet Survey Satellite. And so one of my first projects as a graduate student was to look at TESS imaging of nearby AGNs to see what their optical fluctuations look like over time. So the great thing about TESS is it has a really high cadence, so we can get minutes time scale light curves from nearby AGNs, but since TESS is designed for exoplanets, that AGN needs to be really bright, but thankfully this object is. So if we go to the next slide, so why NGC 4395? Well, it's nearby, it's super bright for an AGN. And it's a well-studied dwarf AGN, meaning it's a dwarf galaxy, so its supermassive black hole mass is only 10 to the 4 to 10 to the 5 solar masses, which is actually pretty wimpy for an AGN. And also it's known anecdotally to have very high amplitude optical variability on nightly timescales, but it hasn't been studied super well. So if we go to the next slide here, I think I have an image. Yeah. So on the right is the light curve. So this is from the TESS satellite. As you can see, the x-axis there is days, so it's about a 1-month light curve. And what you can see is that it's unlike a supernova light curve or another transient, in that its variability is stochastic. So this has been known for AGNs for a while, but what we've done is we've modeled this variability using something called a damped random walk, which is shown in the blue model there. And even though it's so stochastic or has random fluctuations, we can measure a characteristic time scale of those fluctuations using this damped random walk modeling. So that's what we've done there. And actually, if we could stay on that slide for just a second. Yeah, so on the left here is the time scale on the y-axis, the log of the time scale, which I call tau, in days versus the black hole mass on the x-axis. And the black data point there on the bottom left is NGC 4395 from the damped random walk modeling. And the magenta data points in that plot are from a previous paper. And so what we can see is that because NGC 4395 has a very low black hole mass, its damping timescale is, or characteristic variability timescale is of the order of a few days, which is much smaller than your typical AGNs in magenta. But if you extrapolate a line through correlation through those data points, it's roughly what you would expect. So the question we have now is there a relation between the black hole mass on the x-axis and the characteristic timescale across this entire range of supermassive black hole masses? Can we confirm that this trend is in fact holds? Because only one data point there, you could make an argument. So we're going to try to fill in the data on this correlation a little better. Next slide, please. Yeah, so here's the result shown in black. The damping timescale or characteristic timescale in days versus the black hole mass. And the black data points there are our results using a wide variety of light curves from the literature, including our TESS NGC 4395 data point and other dwarf AGNs from the literature and nearby Seyfert galaxies from reverberation mapping programs. And we've also combined light curves going back 20 years for SDSS quasars, which are the cluster of data points on the top right, which have more massive black hole masses. And what you can see is that there's, in fact, the correlation holds true when you add more data points, and the correlation looks very different than the red data points there, which are from another paper looking at X-ray variability timescales and light curves. So we think because the slopes are different between the X-ray and optical, that this indicates that the optical variability has a different origin and probably rules out some models for simple X-ray reprocessing of the optical variability. So next slide, please. Yeah, so how can we interpret this variability relation? So to do that, we've used this equation on the bottom in black there, and we've assumed that the accretion disk is just a Keplerian disk. And when you do that, you can convert that damping timescale tau into a radius using that proportionality. And so this is plotting radius now versus black hole mass. And our relation is shown in the orange line there with 1 sigma uncertainty. And when you do that, and you plot the correlation here in blue, this is from microlensing observations of accretion disks. And what happens is if there's a microlensing event in an AGN, you can get using the microlensing equations, a characteristic radius of the disk in the optical. And we find that our characteristic radius corresponding to the characteristic timescale of the variability is consistent with the microlensing observations. But our correlation probes black hole masses over the entire range of supermassive black holes, whereas the microlensing observations have only so far been done in quasars. So that's very reassuring. And finally, you can actually go one step further because these relations have another factor of alpha, which is the viscosity in the accretion disk. And what we found is that the normalization of this plot is consistent with a 5% level of dimensionless viscosity, which corresponds to a thermal variability timescale of thermal perturbations in the accretion disk. So that's, we think, confirms one possibility that people have considered for the optical variability in accretion disks. And if we go to the next slide, so this is the last point I'll make in this talk. This is again, going back to the characteristic timescale on the y-axis versus mass. We thought, well, why stop at AGNs? What happens when we extend this to stellar mass accretion disks? So in the magenta points there are white dwarf accretion disks, optical variability of white dwarfs from Scaringhi et al. 2015. And when you extend our relation down to those masses, stellar masses, we've found that our correlation is consistent with those observations within about 2 sigma, which we think can easily be explained by some simple selection effects of our sample. And so we think this indicates that the optical variability, because it spans this entire range of masses, could be intrinsic to the accretion disk itself, which is the size of that accretion disk is connected to the mass. And so that hints that the relation could be universal across all accretion disks. And we think finally, if I have one more slide here, same slide, but one. I think there might be one. Yes, so here. So in between is the missing link between stellar mass black holes, or stellar mass accretion disks, and supermassive black hole accretion disks. And so we think in between this missing gap in the plot, there should lie a population of black holes called intermediate mass black holes, which are traditionally very difficult to observe, in part because their luminosities are very low. So we think that one possibility is that this could be a powerful new tool using optical variability to identify intermediate mass black holes. And if we can measure their variability timescales, then it could be a new probe of the masses of intermediate mass black holes. So exciting possibilities for the near future. So, thank you.
Maybe I'll start. So it would seem that accretion disks ought to be. It would seem that accretion disks ought to be often quite different. So this suggests some commonality to accretion disks that might be surprising. Could you comment on that?
Yeah, so to some extent there is maybe a simple geometric relation just between the mass of the black hole and the size of the accretion disk. So we think that's probably what this is probing. So yeah, that's just the standard model of accretion disks. There is, the accretion rate, or the Eddington luminosity ratio. And sort of all of these AGNs have a similar range of accretion rates, because if it's too low, then we can't really observe it that well, and there aren't that many that are like close to Eddington. So there could be a dependence on the accretion rate that we're not seeing in this sample, but that could be a contributing factor to the scatter and the relation.
Okay, so for things like nova, you expect the accretion disk to have a lot of dust, presumably. Mm-hmm. And I was wondering whether you see a relationship like you've shown for the X-ray versus optical, for if the time scale goes away as you go further into the infrared when you're looking through the dust.
Yeah, in the infrared, to my knowledge, that hasn't been looked at, but for individual objects, the variability in the infrared looks similar. So I suppose if that infrared variability is just a reprocessing of the optical emission, then I would expect the correlation would hold. But we haven't looked at that yet. Yeah, but good question.
Sorry, what do you mean by nova-like white dwarfs? Novae or dwarf novae? So white dwarfs with accretion disks. So
yeah, these are nova-like white dwarfs, like in their rapidly accreting state.
Okay, so something like dwarf novae. I'm just curious because, ultraviolet emission is going just from the very inner part of accretion disk or even from the surface. Yes, and do we can we have the same physics of variability in the case of very large accretion disk with ultraviolet emission coming from outer parts of the disk and white dwarfs where it burns just near the surface?
Yeah, so it's a good question. People have looked at like the wavelength dependence of the variability timescales. At least for AGNs, I can't speak to stellar mass systems that well. But in AGNs, the wavelength dependence, so you would think that that would be moving, as you observe in different filters, you would be probing different regions of the disk. But it turns out the timescales that you get are roughly the same. So we think this means somehow the variability in the inner parts of the accretion disk can be communicated to the outer parts of the accretion disk. And there are some models that might explain why, but we don't know. We don't know why. Yeah.
We have to move on.
Thank you.
Sorry.
Yes.
But thanks so much, Colin. Okay, so our next talk is by Rachel Harrison, who's a fifth-year graduate student in astronomy. Rachel's going to tell us about protoplanetary disk polarization at multiple wavelengths. I believe that you should be able to control the slides with
just
cursors.
the arrow keys?
Yeah, the arrow keys, yeah. Okay.
Thanks. So my work focuses on protoplanetary disks, which are the disk of gas and dust that surrounds a planetary system as it's forming. So over the past 20 years, we've observed a huge amount of diversity in exoplanet systems in terms of the sizes, compositions, and orbital radii of the planets. So the big picture question that I'm interested in is, where does this diversity start? Can we already see differences between the protoplanetary disks that are the progenitors of planetary systems in terms of their dust populations? Every planet and exoplanet starts off as dust and gas in a protoplanetary disk, and that dust emits blackbody radiation at millimeter and submillimeter wavelengths. And ALMA is a really good telescope to use to look at that dust emission. And the thing that I focus on in my research is determining the sizes of dust grains in disks like these, because rates of dust grain growth have important implications for the mass available for planet formation and planet formation timescales. So one of the ways we can learn more about the dust in a disk is to look at its polarized emission. So this is HL Tau, which was the first protoplanetary disk to be observed in polarization at multiple wavelengths. And in these plots, the gray contours represent total intensity, blue shading is polarized intensity, and the red vectors correspond to the direction of polarization, and they're scaled so that their length corresponds to the polarization fraction. So you can see that the source looks very different in polarization at these different wavelengths, and we think that that's because different mechanisms are dominating the polarized emission at these different wavelengths. So at 870 microns, that pattern with the direction of polarization along the disk's minor axis is consistent with self-scattering. And then at 3 millimeters, we think that this azimuthal polarization pattern is produced by elongated dust grains that have been aligned by some force in the disk, possibly radiative alignment torques from the radiation anisotropy, or aerodynamic interactions between the gas and dust. And then at an intermediate wavelength, we see something that looks like a combination of those two patterns. Scattering polarization is especially interesting because it can give you an estimate of dust grain sizes that's independent of estimates from continuum observations of the spectral index. So polarization from scattering is most efficient when the maximum dust grain size is about lambda over 2 pi, where lambda is the observing wavelength. And in this chart on the bottom right, you can see that as you go to larger maximum dust grain sizes, the wavelength where the polarization fraction peaks gets longer. So by looking at a disk at multiple wavelengths in polarization, you can determine where the polarization fraction from scattering peaks and get an estimate of the dust grain size. So after we saw those very different polarization patterns in HL tau at different wavelengths, the first question we wanted to ask is whether that pattern is the same for all protoplanetary disks. And the answer, it turns out, is no. So these are images that I've made of 4 different protoplanetary disks in polarization. The black contours, again, represent total intensity. The blue lines represent the direction of polarization at 3 millimeters, and the red lines are the direction of polarization at 870 microns. So you can see that HARO 613 and V892 tau at 3 millimeters have that azimuthal polarization pattern that HL tau had at that wavelength, whereas RY tau and MWC 480 look more consistent with scattering at 3 millimeters. And then at 870 microns, the polarization pattern in all these disks is consistent with scattering. So now I'm working with my theoretical collaborators to model the polarization that we would expect to see from scattering in these sources. And we're using models that consider a couple different types of dust population. The first is a single dust grain population where the dust grain size distribution is described by a power law with a single maximum dust grain size. And then we vary the dust grain sizes and optical depths and look at the resulting polarization and compare that to our data. Then in the 2 population model, we've got a disk that hosts both small dust grains that efficiently scatter light at shorter wavelengths and large dust grains that scatter efficiently at longer wavelengths. And then differential settling leads to this kind of dust sandwich where you've got larger grains settled towards the midplane and smaller dust grains above and below the midplane. And I want to zoom in here on the case of RY tau, since that's the disk where we have the strongest evidence for scattering at both wavelengths. On the left, we've got the data in the scatter plot compared to several different single grain models with different maximum dust grain sizes, and the right shows the 2 population model. So the key features that we're trying to reproduce with this initial round of modeling are the fact that we have a significant polarization fraction at both 3 millimeters and 870 microns, and the fact that in the center of the disk, the polarization fraction is higher at 3 millimeters. So the model that best reproduces those features is the one with a maximum dust grain size of 200 microns, although that model does predict a polarization fraction lower than what we actually see in the data. So to wrap up, we've shown that disks can exhibit different polarization patterns at the same wavelength, and also different transitions between polarization patterns at different wavelengths. So this is evidence that there are multiple different sources of polarized emission in protoplanetary disks, and this could also indicate differences between the disk's dust grain populations, since polarization morphology and fraction are so sensitive to dust properties. In the future, I'm going to be working on investigating the relationship between dust grain growth and disk substructure using high-resolution observations. And I'm also going to be expanding the sample of disks with multi-wavelength polarization observations so we can learn more about the correlations between polarization and other disk properties. So with that, I'll take any questions.
Questions for Rachel?
How do you take into account possible differences in, say, timescale? Like, could different patterns be from different points in the disk evolution?
Sorry, could different, what be from different?
Could different polarization patterns, could they be at different points in the evolution of the disk?
Yeah, so that's kind of an open question at this point, and it's something I'm really interested in. And that's one of the reasons that I want to expand the number of disks with multi-wavelength polarization observations so we can look for correlations between those polarization patterns and disk age to see if, for example, we can get a handle on rates of dust grain growth and whether those rates are different for different disks.
Questions? All right, let's thank Rachel again. Okay, so next up we have Ian Brunton. Ian is an undergraduate astronomy major working with Professor Brian Fields, and he's going to be telling us about the threat assessment from X-ray supernovae.
All right, cool. Thank you, Professor Wong. So what we're going to be talking about here is the X-ray energetics from supernova, and specifically how they can potentially impact Earth-like planets. Now, I did this research along with my fellow student, Connor O'Mahony, and we're working under Professor Brian Fields, who I'm sure all of you know has done a lot of work in this field already. But what we're doing here is kind of like looking at that work and shifting the focus to the X-ray energies in particular. So just to give a real quick recap as to how supernova in general can impact Earth-like atmosphere. Basically, we just got our Earth here that's developed its ozone layer to protect it from the sun. And as you guys know, supernovas, when they blow up, they emit extremely ionizing radiation, like going through space. And if that's close enough to the Earth, it can actually interact with the Earth's atmosphere, break down its layer of defense, and the sun rays come in, the higher UVB energy rays come in and zap the biosphere, okay? So it's not actually the X-rays that are going to be reaching the ground. You're still going to have to go to the doctor's office to get an X-ray scan if that's what you're looking for. That ozone depletion we're talking about, the way we kind of parameterize that to say whether or not it's deadly or not, we use this term called the kill radius, which that's basically just the distance at which we would start potentially seeing almost extinction level events, or at least severe disruptions to the biosphere. And that's a function itself of the ozone depletion. And so previous calculations through the last 20, 30 years when they've looked at supernova have kind of put this estimate around 10 parsecs, give or take, depending on the certain model. But that number has kind of been entirely based on the cosmic rays and a little bit of the gamma rays. And the reason we're kind of looking now at the X-rays is because we, through the past 2 decades or so, through our X-ray astronomy, we've gained a little more insight into how energetic supernovas can be in the X-rays. So we want to see if that's going to change that 10 parsec estimate at all for that kill distance. And you might want to ask, okay, well, are they even energetic enough to start that ozone depletion? And there's a bunch of atmospheric chemistry that goes into this. But this is Astrofest, not Atmosfest, so let's just get to the explosions. Okay, cool. So how can a supernova actually emit in the X-rays? Well, before they even die, some stars can actually start shedding mass. And that mass that builds up kind of builds this dense circumstellar medium surrounding the star, so that when it actually does blow up and it does have that huge explosion, that material collides with each other, heating up that material, which we then see on the other end as a thermal emission in the X-rays, all right? So that's what this schematic right here kind of is. And this right here is just a simple X-ray light curve that we see with a typical supernova like this. Got your luminosity logged here versus the time since the explosion in days. And real cool to note about this is just the emissions for these X-rays last months to years after the explosion. This isn't just the initial explosion that's blowing off. And that's going to be important when we start considering how deadly they can be to a planet like ours. Okay, so this slide's a bit busy, I know, but basically this is the same plot I just showed you now with all the X-ray supernova that we looked at, about 20 of them. And the cool thing to note is here I've grouped them by type, so you can clearly see the disparity between those that have that dense circumstellar medium and those that don't. That's important. Another thing I want to point out here on this slide too is that like 90% of our data is all from these 3 telescopes right here, which at this time can only really see in that soft X-ray band. And that's important because that energy that's being deposited into the atmosphere, how we calculate the actual deadliness of that is kind of dependent on that photon energy level. And we're strictly keeping it to the soft X-ray band here because all we want to do is see if that 10 parsec estimate is somewhat accurate. So to keep that in mind when we go through the calculations here. So again, this is the same graph, just luminosity versus time, which is now logged on the x-axis, so you can really see like how long some of these bursts go for. So the first step to try to parameterize how deadly these things are, just get the total energy. That's just area under the curve. This is just the luminosity integrated over time. And another thing to note is you may see these trends kind of developing the light curves and say like, oh, well, even though you don't have observations for that time, why not extend that out to here and say it's actually, more energetic than it's showing? We didn't do that. We just want to see if we're getting somewhat around that 10 parsecs initially. So these are very conservative calculations we're making. Step 2, that's just that 400 kilojoules per meter squared is just the energy you need deposited in the atmosphere by a soft X-ray photon. And in that equation, laser pointer died, but that's all right. The total X-ray energy over the surface area of the sphere is basically going to give you that energy deposited in the atmosphere. And since you've got that radius in the denominator there, that's basically just what we do to solve for the kill radius, which ends up just being a function of the total X-ray energy output and that fluence that's being deposited into the atmosphere. So now on to our results, which we're pretty excited about these. Okay, so again, keeping in mind how conservative we kind of were with these estimates, soft X-ray energies, not extrapolating any further on their trends, we're already getting kill radii that are some 2, 3, 4 times higher than the initial estimate. So I think that's pretty cool. Bigger's always better, bigger's always cooler. And then keeping in mind too, even these lower ones down here that are below 10 parsecs, they're still going to have an impact on a planetary climate in some way. This kill radius is kind of built in to be almost like extinction level, or at least severe impacts on the biosphere. So basically what this slide shows you is just how deadly and how much this possibly changes our, what we know about supernova and how they can impact life. And this kind of just summarizes everything I was saying. I know I kind of flew through a bunch of data and everything, but I was excited to get you to the results. Left up the plots there that we have. And what we'd like to do in the future is, potentially look at other X-ray transients in the universe, because these obviously aren't the only things emitting in the X-rays. And then to possibly just model these on paleoclimate models so we can see how potentially this could have impacted Earth at some time in the past. And so just to sum up, bigger's better, right? So it's cool. Any questions?
So obviously the Earth has had several major extinction events. Do you know if any of those, or if there are any theories that those might have been caused by supernovae? Mm-hmm.
Yeah, so actually Professor Brian Fields, who kind of ran our research, he's done a lot of work on that, and there's actually a lot. The most recent nearby supernova that would have actually affected Earth would have been about 2.5 million years ago. And around that time, we do see a significant drop in certain foraminifera in the oceans. And then even going back further, there's one about 500 million years ago in which they linked it as well to what's called the Ordovician extinction. There's a lot of work being done in that area, and there's definitely links. And they actually found radioactive material from a supernova in deep sea sediments, that was just a couple of years ago. Pretty exciting stuff.
If I might ask a question.
Yeah.
Speak to the mic. Go ahead. Okay. So there seem to be quite a few massive stars within that distance, like maybe Sirius or whatever. Is there a concern that we should be worried about some of those stars?
No, at least not in any future scenario. I mean, I guess if humans last that long, then yeah, we could look into it. But and maybe we won't have to go through the TSA scanners to get X-rayed. That would be nice. But no, there shouldn't be anything anytime soon.
Okay, so our next speaker is Jamila Taki, and she's a graduate student in the Electrical and Computer Engineering department, but has been working with Professor Athol Kemble, and she's going to tell us about work on exoplanets.
Oh, how do I? Is it up?
You can use the cursors.
I think it's. Oh, okay. Sorry, I don't know how to use a MacBook. Is this on someone else's?
Just hit the space bar.
Oh.
Oh, it's showing the other presentation. I think that's the confusion.
Oh, well, hit the space bar, it should go. Yeah,
Ah, okay.
just look up.
Oh,
Yeah,
okay,
so just
cool.
look there.
Thank you. Okay, so I work on statistical methods for exoplanet transit detection, and today I'm going to talk about the application of those methods for searching the first 3 years of TESS short cadence light curves. Okay, so TESS and Kepler operate at a really high level of sensitivity necessary to detect the brief dip in brightness as an exoplanet orbits its host star. However, the downside is that observations are often corrupted by instrumental or environmental noise sources, and these noise sources can often mimic or conceal a transit signal if it's present in a light curve. And so these noise sources are termed systematics, and I'm just going to refer to them as systematics from now on. So a typical transit detection pipeline, such as the NASA pipeline, will try to handle systematics by forming an estimate of them and removing them from a light curve prior to transit signal detection. However, we show in our prior work that by doing this and not knowing if a transit is present in a light curve, you may inadvertently overfit a transit signal if it is present and remove it from the data and have a lower overall detection rate. So we developed a method where you can perform transit signal detection on a light curve which contains systematics. So to do so, we need some kind of model for a light curve, and this is kind of a fairly standard model in the literature, but basically we posit that a light curve Y is a additive combination of systematics, termed S, unknown stellar variability, termed N, and an unknown candidate transit signal, termed T. And yes, the systematics are also a priori unknown. So transit detection is posed as a binary hypothesis test for a candidate transit signal T among a family of transits that might be possible in a light curve. And so in the null hypothesis, we model the light curve as just containing two unknown noise sources, systematics and stellar variability. And then the alternate hypothesis, we posit that there may also be a transit signal present. And then detection is the way in which you detect a candidate transit is you ask which which model best explains the data, the alternate hypothesis that the light curve contains a transit, or the null hypothesis. And you compute a likelihood ratio test. And essentially, in a transit search, you do this for over the range of possible candidate transit signals, broken down by period, epoch, and transit duration. Okay, so I said that the systematics and the stellar variability are a priori unknown. However, you can generally constrain their properties and infer their kind of general form from the collection of light curves that you observe on the sensor and any kind of prior physical knowledge that you might have. So in our treatment, we treat them, we use Bayesian priors to describe their unknown form. And to compute this likelihood ratio test, you need to compute the likelihood of observing the light curve under the Ivar hypothesis model. So to compute that quantity, we marginalize over these Bayesian priors which we're using to describe the unknown form of systematics and stellar variability. So essentially, we marginalize over a range of continuous models, and the main takeaway from this slide is that we use Gaussian priors to describe these unknown noise sources, and the nice benefit of that is that these two added together unknown noise terms have nice analytic marginals, and so the final detector that we get has a nice analytic form which only depends on the joint covariance of the unknown systematics and the unknown stellar variability. So CZ in that bottom equation represents the added stellar variability covariance and systematic noise covariance. Okay, So in prior work, we applied this method we developed to a small subset of Kepler light curves from that were collected at a 30-minute cadence. However, in this work, we really wanted to scale up and see, can we actually find exoplanets, and how well does this method work? So we applied our pipeline to the first 3 years of TESS short cadence data. Now, the interesting thing about TESS is it doesn't continuously observe the same region of sky for a full year. It rotates around every 30 days and observes a different region around like either the North or South Pole. So we only looked at targets that were continuously observed for the full year, and that's roughly 10% of the observations. So there are major differences between Kepler and TESS data, and one of them is the scaling in complexity. That a light curve has roughly 10 to the 6 data samples, and the transit search space itself massively increases because the transit search space depends on the length of the non-linearly on the length of a light curve. So this represents many more likelihood detection tests that we had to compute. And we completed this using a Blue Waters allocation. Another major difference is that TESS has a huge amount of missing data or bad data. And on that figure on the left, each block represents a day, and the darker color represents the density of missing data. So a very dark color means that all the data is almost completely missing from that day. And you can see that roughly, and so every row represents 30 days or a sector of observations. And you can see that roughly every 14 days, there's a day-long data chunk that is missing from light curves. Now, one of the major benefits of our pipeline is that it doesn't require any gap filling or stitching or anything like that, because we only define our model over the data points that are present. And that means that you're not biasing your results by including fake data in the resulting detection test. Okay. So here's an example light curve, just so you can get an idea for what I'm talking about. The first, the left-hand side represents a year of data, and the right-hand side represents just 60 days. And this light curve has a really nice and clearly visible 3-day transit, but most transits are not this clear. Now, another systematic feature that is different about TESS data is that they have this momentum dump cycle. So Kepler would have this huge kind of flux accumulation that would occur and lead to these really high-level systematics. Whereas TESS, every 5 to 6 days, will dump its momentum, dump its flux and or energy accumulated, and so it has these kind of periodic dips that occur in the data, and you can't really see them very well here, but it leads to a lot of kind of spurious detections because the way those flux dips looks a lot like transit signals. Okay, so. The goal of this work in general was to scale up the method and apply it to test data to see is it feasible to use this? I mean, the detector complexity is higher than a standard kind of approach. And also, how does it work differently on a different kind of data set? Like what issues in the data cause differing results? And the second major goal is to actually find some exoplanets. But we need some way to say, is this pipeline actually doing what it should be? Is it actually finding exoplanets? So we have two methods of validation. The first is that we look at our rate of test objects of interest recovery. And when I say recovery, I mean, is the leading transit that we find for a light curve identical to that of the test object of interest in its transit parameters? And we, in general, have quite a high rate of recovery. We have 65% of test objects of interest are recovered. And this is with a higher detection threshold, so we don't expect a full 100% recovery. So we use a threshold of 10, and TESS uses like 7.5. So yeah, there are only 100 test objects of interest in the 4,000 or so light curves that we look at. And our recovery is slightly higher relatively for longer orbital periods. And then the second thing we do is injection tests, and that's where you simulate a transit and you add it into a light curve, and then you run your pipeline over that data and look at your recovery rate. And in general, we have a high recovery rate, roughly 80%, but with a slight dearth in detections in the 5 to 10 day orbital period range. And I think that that's likely due to false alarms induced by the form of systematics that are specific to tests, i.e. the momentum dump cycle. And we have all these methods for filtering false alarms, but I don't have much time to talk about them, so just going to leave it at one example. This is an even odd plot, which you use to eliminate eclipsing binaries, because you don't expect the even cadences and the odd cadences phase folded to have the same transit depth. So this actually is a real transit, and it's a 56-day transit, and it's one of the test objects of interest. Okay, that's all.
Can you go back to the previous slide?
I'll try to, but okay, yeah.
Okay, so I was actually a little bit surprised that you had increased recovery for longer periods. I would expect that you would have a better chance with the shorter periods, since there would be more periods in a given light curve. Do you have any idea why you have increased recovery for such periods?
Yeah, I think it's mainly due to the kind of form of systematics in the data. There's a lot of kind of periodic systematics that occur on a short time scale. So every time that they have this momentum flux dump, some data goes missing, but before and after it, the light curve undergoes a little flux ramp, and that can lead to a really high rate of false alarms in that range. So those false alarms will kind of overshadow the true transits, possibly leading to a misdetection. Though I think that it's a little bit more complicated than that. But yeah, there's a whole host of problems that can go wrong, essentially.
Thank you.
So what are the prospects of deploying this system in a way that will quickly maybe discover new objects in a way that might produce some very exciting publicity for your research?
So we're actually looking through all of the detected objects at the moment to see if any of them are interesting, or and we have a bunch of filtering methods, as I said. So hopefully there may be something there, but as of now, I'm not confident that I can say, oh, this is a real transit and not just some kind of false alarm. Thank you.
Okay, so I think we are actually a little bit ahead of schedule, which is excellent. So our last speaker today is Professor Joaquin Vieira in the Physics and Astronomy departments, and he's also the astronomy lead here at NCSA. And, we have your talk, excellent. So he's also director of CAPS, and he'll be telling us a bit about what it's been doing.
All right. I'm going to talk about CAPS. Sorry, okay, that works. Okay, I'm going to briefly just tell you what CAPS is, what we do, who we are, and then I think the pertinent thing is what resources are available for you, the audience. So CAPS is a center within, so NCSA is this institution. CAPS is a center within NCSA. I guess I can't wander from here, huh? And the goal of CAPS is to kind of lay the foundation for future expertise and leadership in survey science, which is broadly defined. Internal or funding comes internally from campus, NCSA Astronomy and Physics, and right now the understanding is that we go until 2025 and then we'll revisit what's going to happen after that. External funding mostly comes from the NSF, but that's not totally exclusive. Resources include, there's 5 graduate student fellowships per year, so every year we give out 5 one-year fellowships. There's 3 postdoctoral fellowships. These are kind of our prized postdocs, they're independent. And 20% of time for NCSA astronomy staff, scientific staff, they can use on science, and so kind of work with you, work with outside projects, whatever. They're independent for that. And then we have computing within the campus cluster that's available for all members. So this is kind of the schematic of how I think of what CAPS is doing. So there are many efforts kind of in general survey science on campus, from the physics department, from the astronomy department, also many different funding agencies and projects. And what we wanted to do was have a kind of one house where everything could meet together and synergize and collaborate and have, coordinate. And so big efforts on the optical, there's DES and LSST. For CMB surveys, we're working on SBT and CMBS4, and there's synergy here between both cosmology and catalogs and transients, and then also multi-messenger astrophysics with like LIGO and IceCube, and particularly transient events and MMA. So projects we're currently working on, dark energy survey, which was at some level kind of one of the foundational projects for NCSA astronomy. Vera Rubin Observatory, our role has evolved, but we were critical for construction and building the prototype for the data facility. South Pole Telescope, we're getting involved in that, particularly for point sources and transients, and building a server for public access. And the idea is that we're kind of leveraging South Pole Telescope to get involved and get a good footprint for CMB Stage 4, which is the next big CMB experiment, jointly funded by DOE and NSF. We're also working on a project called SIMA, which is scalable infrastructure for multi-messenger astrophysics. We're getting involved in software readout and control for next generation long wavelength detectors. And we've been engaging with ground-based radio surveys. So these are the kind of things currently on our horizon, but not exhaustive. And if you have ideas, come talk to us. So who we are, so I'm director of the center. Gautam is deputy director. We also have project management support, which Michelle Butler, who's been critical to all of this. She's retiring, and so Jay Alameda is about to become the associate director. And then Steve Petrovich is lead research programmer and also point person for LSST. Within the staff, so the staff within CAPS includes 4 research scientists, 3 research programmers, and 3 project managers. What we do, we have a weekly coordinating meeting that usually includes the postdoctoral fellows, and we coordinate activities and strategize about what we're doing in the future. And you may remember we had a weekly seminar every Friday here that kind of went on hold for the pandemic and also just Zoom fatigue. But we're going to be restarting those in the fall. And we have some visitors starting up this in May, so stay tuned. There'll be some emails about those. And you'll see a lot of these people are in the room, so say hello. Affiliated faculty, these are the 16 affiliated faculty. It's a loose confederation, basically, if you want to be involved, and there's a reason that's it. It's inclusive. But there's 6 faculty members, so about half the department from astronomy is involved. There's 7 faculty in physics, 1 faculty member in aerospace, 1 even in business. In terms of broader community engagement, we were a sponsor for the Cosmo 21 scientific conference, which turned out to be online, but and we've also hosted and are hosting numerous LSST, dark energy survey collaboration, and CMBS4 meetings. So we can use CAPS as a venue to kind of reach out to broader community engagement. I think of it as the kind of core of the center are the postdoctoral fellows. So every year we hire 1 postdoctoral fellow. There's a 3-year appointment. They're independent. It's expected and understood that they're going to be working kind of within that Venn diagram I showed you of what projects and strategic interests we have, but we leave them alone and they just get to make science. We have the fellows choose a faculty mentor just because we don't want them to be not looked after, and a home department. So again, the home department sometimes is astronomy, sometimes it's physics, sometimes it's NCSA, they choose. The fellows have been extremely engaged with NCSA and CAPS and are leading scientific efforts and new initiatives, and it's been going fantastic, and we're really pleased and happy to have all of them here. So Monica was the first one. She actually left a year early because she got a permanent position at Gemini. Deep is the current fellow. He's been working with Nico Yunus and working on LIGO and MMA, among other things. Srini is the latest faculty member. Because of pandemic, he's not actually physically here yet. He's still remotely, but he'll be coming this summer. His faculty mentor is Gil Holder, and he works on SBT and CMBS4. And then we have an offer out to the new fellow who is in the room. So say hello to her. Okay, graduate student fellowships. These are open to any graduate student on campus working in the field of astrophysical surveys, and this is broadly defined. I mean, if you can make a case, you can get a fellowship. There are 5 graduate fellowships annually, so every year we have a competition for 5 spots, and there's a fellowship for 1 year. The idea of this is that we wanted it to be dynamic and be able to, pivot and be responsive to what we needed as a center and what students were doing. The application is meant to be not onerous. It's just a CV, a 2-page research statement, just doesn't need to be long, and arranged for 2 letters. It's usually good to have like one from your faculty mentor and one from, say, NCSA or the person you'd be working with. A committee reads and ranks all the proposals. For the most part, we just go down the list of ranking, but there's also programmatic considerations. Last year, we received 13 applications for 5 spots, so that, the odds are good. That's, I would say, low, because typically there's kind of informal pre-vetting by faculty. There's kind of an understanding that one faculty member is going to get 1 graduate student just because we want to spread it out, not concentrate it in certain faculty. One of the 5 spots we set aside for theory in collaboration with ACASU, the New Physics Center of Fundamental Physics in the physics department. And the best path for one of these is to engage with current efforts and people within CAPS already. Look for next year's call for applications will be in a few weeks, and the deadline will be in June, roughly. So these are the fellows we've had. Like there's some, you can't get it multiple times. Some people have, but we also try to, spread it out and, make sure we have a diverse pool. We have computing resources. Part of the center was we have a $100,000 a year budget for building up computing. So the idea is, each year we kind of assess what we need, and usually that is changing. But the idea is to provide a big sandbox for campus affiliates working on synergistic activities to have computing resources. Okay, and then have a computing resource to allocate strategically to important projects. Like for instance, we're building this server for SBT, but the idea is that now we have built it for the next big project already, and we have that expertise. So our first purchase, we got kind of run-of-the-mill nodes, 10 nodes, so 400 cores. Our second purchase was 2 nodes of very high memory. These were kind of optimized for some stuff with CMB map making. We also have Radiant server and some storage. These are the usages just to see kind of who's engaged and who's using it. For the most part, it's not heavily subscribed, or it's not maxed out. So if you need compute, come talk to us. Scientific outcomes. So I didn't update this, but this was from a year ago. So we're finally seeing affiliations show up for CAPS. Colin's paper was one of our highlights. We were really excited to see that and to see the CAPS affiliations there. We ask, if you are a fellow or using somehow resources from CAPS, we ask that you add CAPS as an affiliation, just so we can kind of keep track of things. So recap. So CAPS is finally at full operational capacity. We kind of had a ramp up. Now we're fully operational. Come and pandemic's almost over, so we'll be moving back to in-person probably in the fall. But we're all around. Come talk to us if you need help or want to collaborate on projects. Sometimes people come to us and it's very much in our wheelhouse of astrophysical surveys. Other times we're kind of informal conduit to other resources at NCSA for things like physics or whatnot, atmospheric sciences. So we are fine working outside of just strictly astrophysical surveys. People often ask, how do you get involved? You just show up. So we have seminars. You can shoot me an email. It's fairly easy. We are inclusive. And more information, and most of what I just showed you is all on our website there at CAPS. So that's all I had. Thanks.
So if I could ask a question, for those of us that are For those of us that are kind of newbies at cluster computing, is there a plan to offer some training or other advice just to sort of help people get started with those techniques?
There are not planned, but we could. I mean, I believe Campus Cluster does stuff, and I know like certain, like Open Science Grid has things like that. I'm pretty sure Exceed also has classes like this, but if there was a, like I said, if you want to get involved, show up, and we can self-organize one of these, and we could do that.
Yeah, excellent. Other questions?
Okay.
Okay.
Thank you.
Thanks a lot, Joaquin. Okay, so before we let you run off for refreshments, I did want to say a few thanks. We've gotten support again from the Vermilion River Research Fund, which is sponsored by the Chu Family Foundation. So a lot of what we've been able to do is thanks to that fund. I'd like to thank Rebecca and Susan in the astronomy front office, who did a lot of the behind the scenes work to make this happen. And so if you see Susan outside, please thank her. I'd also like to thank Amanda and Nick, who helped me on the organizing, and Rukmani, who came out to be with us, and all of you, of course. And so, and also the folks in the NCSA events who have been helping us with the audiovisual. So hope you enjoy the poster session. Please don't leave. There's a lot more science to talk about. And please, if you'd like to recycle your name tags, there's a drop box outside you'll find as well. Okay, thanks everyone.